So example 2, it's asking you to determine for concave up and down, so that means we need to find the second derivative. And it's also asking you to justify, so we'll get into that in a second. But to start, I got to find the first derivative, and there's no way around it. In this particular case, you have to use the quotient rule. So remember, ho d high minus high d ho, draw the line and square below. So and then we got to do a little bit of simplification. So distribute the 2x in the numerator and combine like terms. And we end up with negative 20x over x squared minus 9 all squared. If you end up with a monomial in the numerator or denominator, rewrite it as and use the product rule rather than to reuse the quotient rule. Now, I couldn't do that in the beginning because you did not have a monomial either in the numerator or the denominator. But in this case, we do end up with that. So the first thing we're going to do is a little bit of a rewrite here. And then I can use the product rule. Sorry, I highlighted this earlier, so this is proof that I have to record this many times before I just get it one good one. And I was trying to show that we end up with, we're using the first times the second, and then I was trying to point out the most common mistake is to forget the using the chain rule here. So right here, what I'm underlining is highlighted in yellow. The 2x, for some reason, everybody forgets. So you have to remember to take the derivative of the interior there. So that's a really common mistake there. Now, I have one option. One option right now, if I'm simplifying, is to factor out the common factor in green, or I could just write them as two separate terms. So for example, I could write them like this here. So I'm just simplifying them, and then I'm going to concentrate on getting a common denominator. And the way to get a common denominator is to multiply the second one here by x squared minus 9 and x squared minus 9, so that we get x squared minus 9 to the third in both of the terms. So we're going to simplify that. Whoops, that was the wrong way around. So that we end up with a common denominator. And then I'm going to do like distribute the 20, do a little bit of factoring if we can to make it simpler. Because the reason why we want to make it simpler is because it's easier, or not simpler, but factored, it's easier to find where the derivative is equal to 0 potentially and where the derivative is undefined. So once we have that, then we need to then say, okay, I have to find where the second derivative is equal to 0. In this case, it happens nowhere because x squared plus 3 is not going to give me any real numbers. So it's not going to be equal to 0 anywhere. And then we're going to look at where it's undefined. Whoops. And it happens to be undefined at where the denominator is equal to 0. But I just wanted you to keep in mind that those are the vertical asymptotes. It changes behavior there, but just so you know that they're not actually part of the graph, okay? So we must still account for the asymptotes since the behavior often changes there. So that's what I wrote here. So then I put them in and I did a number line analysis. So I have to figure out where we have positive and negative values. So, and I'm checking the positive and negative values for the second derivative. So that's why I'm substituting in. I picked negative 4, 0, and 4. I mean, again, you could pick negative 10 and 1 and positive 10 if you wanted to, as long as they're in the interval and not an endpoint of an interval. And then substitute in. And all we care about is really the sign. So you don't have to go all the way to the end and simplify this. You just need to know it's positive. I can see the numerator ends up being positive. For this first one here is the numerator is positive, and then the denominator is going to be 16 minus 9. It's just a positive cubed. It's also positive. So I end up having a positive over a positive. For the second one, I end up with 60 times 3 is a positive, and then we have negative 9 cubed, which is a negative. So now we have a positive over a negative. That's how we got a negative. And the same for the last one. I'm just checking signs, so don't overwork that part of it. So we end up with positives and negatives in that case. And then I'm ready to determine if I have concave up and concave down functions. So here, whoops, we would say f of x is concave up on the interval from negative infinity to negative 3, union 3 to infinity. since f double prime is greater than 0. And that's my justification here. And I've shown all the work to prove it. So all of those pieces need to be part of it. Obviously, this writing here that I added as a note you don't need, but all the other pieces need to be there. And the one thing I just want to point out is concavity is always on an open interval. You can never have it at an endpoint. Now, before when we did increasing and decreasing sets, we're comparing 2 points. Concavity technically is comparing 3 points. We're seeing if we're going up and then back down to a third point. That's why you can't have concavity at an endpoint. Because at an endpoint, I would need to know what happens on the other end side of that endpoint, which is there's nothing there. So therefore, we can't determine concavity at an endpoint. It's always at comparing 3 points. Whereas for increasing and decreasing, you can do that because it's only comparing 2 points. All right, I want you to pause the video and try B on your own right now. So try B on your own. Pause it and then come back and I'll reveal here all of the work with the justification.